Okay, let's start our laws of exponent review. I am using this video tutorial for both my Algebra 1 and my pre-calc class as we learned about exponents way back in middle school. But it's really important to review these laws because we use them even in calculus. So here we go. At some point in time, someone came up with a shortcut way of representing what we just wrote. Instead of writing x times x times x times x times x times x times x, they realized, oh, there's 7 x's we're multiplying together, and we can write it using this notation. Much better, don't you think? Especially if we had like x to the 321st power. As far as vocab goes, you need to know that you've got a base number and you've got an exponent. And here we go. We've got the product rule, and I want to explain real quickly where the product rule comes from. Imagine that you have x squared times x cubed. If you didn't have the power rule, you would just say to yourself, well, let's see, x squared is x times x, and x cubed is x times x times x. So let's see, altogether I have 1, 2, 3, 4, 5. I have x to the 5th. So it makes sense, doing it the long way, that the shortcut way would be we add our exponents. When we are multiplying and the bases are the same, we add our exponents to get our answer. So let's say we had, let's do another one. Let's say we had x to the 5th times x squared times x to the 4th. Same base, so we're going to rewrite our base, and we'll add our powers because we are multiplying, and when we multiply, we add our exponents. So we'll have 5 plus 2 is 7 plus 4 is 11. Or wonder if we had x squared times x to the 10th power. We would, once again, same base, we'd add our powers, so we add our exponents, so 2 plus 10 is 12. Do you need to have that memorized? Yes. Just like you have it memorized how you brush your teeth every morning. Hopefully you do that. All right, quotient rule, same thing. At some point in time, maybe you've seen and I'm always going to use x's just because they're comfortable to us. Obviously, they use a's and m's. I'm just using x's. Wonder if I had x to the 5th divided by x cubed. Well, if I wrote it out the long way, in the numerator, I'd have x times x times x times x times x. And in the denominator, I'd have x times x times x. And I realized that every x over x is equal to 1, right? Anything over itself equals 1. So that's why they cancel each other out. X over x equals 1. X over x equals 1, x over x equals 1. 1 times 1 times 1 is 1. That's why we can just say they cancel out. And what do we have left? We have x squared. Well, because of that, the rule, someone decided, well, wait a minute, that creates a rule there, doesn't it? Whenever we're dividing two things that have the same base, we take their exponents and we subtract it. We take the exponent on the top and we subtract it from the exponent on the bottom, which gives us x squared. So we don't have to do it the long way. However, doing it the long way helps us to remember why we have that rule. I don't know about you, but especially, well, really all the time, I don't like anyone handing down a rule that I don't understand why it exists. So now we understand why that exists. Then we're going to look to the power rule next. And the power rule is just saying when we have a power to a power. For instance, when we have x squared to the 3rd power. If we're going to do this the long way, this means that we have x squared times x squared. I can either use a dot or these parentheses, of course, to represent multiplication. And then if we were going to take it longer, each x squared would be an x times x times x times x times x times x. And how many x's do we have multiplied by itself? We have 6, so that's x to the 6th. And then we can see how the rule comes from just doing it the long way. We can say, oh, when we have, there's just one base, but a power raised to another power, we take that power and then we multiply it by the power it's raised to. So that gives us x to the 6th. So we can remember when we have a power raised to a power, we are multiplying. I guess we could do an example besides that. X to the fourth raised to the third is going to give us x to the 12th. Of course, we could have fractional exponents, but for this quick basic review, we're not going to talk about that at the moment. All right, let's see, power of a product. So if we have, they use a and b, I'm going to use xy to the third power. This third power says this xy is being multiplied by itself 3 times. So I could write it the long way and say, well, we have xy times xy times xy. And then I could remind myself, well, if I wanted to, this is all multiplication, I could just write it like this, right? And then I can say, if it's just multiplication, I'm going to put the x's together and I put the y's together because I'm allowed to rearrange that way when I'm multiplying. And then I can notice I have 3 x's multiplied by each other, so that's x cubed. 3 y's multiplied by each other, that's y cubed. So the long way makes sense, but it's a long way. And so what we want to remember is that when we have when we have a product of 2 or more things, this exponent goes to both the x and the y. I hate to say the word distributing, but it kind of is like that. I call it fake distributing. So wonder if we have something like, let's make it a little bit more difficult. What if we have 4xy cubed? Well, this cube goes to everybody. It goes to the 4, so 4 cubed, that's 4 times 4 times 4, that's going to give me 64. It goes to the x, that gives me x to the fourth, x to the third, because that is the third power. And it goes to the y, so that's y to the third. Let's try something a little bit more complicated. How about if we have 2x squared y to the fourth raised to the fifth? All right, so this 5 goes to everybody. It goes to the 2. 2 to the fifth means 2 times 2 times 2 times 2 times 2. When you do that in your calculator or your head, you get 32. And then watch, this goes to this. Okay, so it is a power to a power. So I know that means x to the 2 times 5, so that would be x to the 10. And then finally to this last one, once again, power to a power. So I know it's going to be y to the 4 times 5, which is y to the 20th. All right, then we've got power of a quotient. So same idea in that I've got xy to the third, okay? Once again, that third is saying that I'm going to take what I see and I'm going to multiply it by itself 3 times, because that's what the exponent of 3 means. And then I can see that x times x times x in the numerator is going to be x cubed, and y times y times y in the denominator is going to be y cubed. That's the long way. The short way just says, hey, this 3 is going to belong to both the x and the y, and we can just write x to the third power, y to the third power. And let's try something that's a little bit more complicated. What if we had 2x cubed over 5y squared? And we're squaring the whole thing. We could do it the long way, but we're going to try to use our shortcuts using our rules. So here we go. This 2 goes to this 2, so it's 2 squared, which is 4. This 2 goes to the x cubed, so I have a power to the power, so it's going to be x to the 6th power. This 2 also goes way down there to the 5, so that's 5 squared, which is 25. And the 2 goes to the y squared, which is y squared squared. Power to power, we're going to multiply, so it's y to the 4th. Sometimes you're going to have negative exponents, and I could go into a long story of where this came from, but I'm just going to go straight to the rule. If we have x to the negative 3, that means it is the same thing as 1 over x to the third power. That's just a rule that you want to memorize, because I'm not going to go into the long reason why. There is a proof, a nice little proof that goes with it. But we can handle that. We can handle that truth, can't we? So it gets a little complicated. Wonder if this is where it gets complicated. Wonder if we had something like 2x to the negative 3. Okay, this x is being raised to the negative 3. But is the 2 being raised to the negative 3? I think not. So the 2 stays up here because 2 is 2. If we put the 2 down in the denominator, that's going to make it a 1/2. And it's not a 1/2, it's a 2. But that x to the negative 3 has to go to the denominator. In math, using a negative exponent is just not polite. It's not good manners. It's like putting your elbows on the table. So when we see that we have a negative, a base raised to a negative exponent, we're going to put it in the denominator. Wonder if, okay, we had something similar. Instead of the 2x to the negative 3, wonder if it was 2x to the negative 3. See how that negative 3 applies to both the 2 and the x? In this case, both would go down like that. And if we wanted to, which we would, we'd want to keep going. And that 3 goes to both the 2, so that'd be 2 to the 3rd power, which is 2 times 2 is 4 times 2 is 8. And that 3 also goes to the x, which would be that. So very different answers, right? Depending on if you have parentheses. If you have parentheses, that negative 3 goes to both the 2 and the x. And in this case, that negative 3 only goes to the x, not to the 2. And you know what? As much as I know that my algebra students need to hear that, my pre-calc students need to hear that as well. So please remember that. Lots of test mistakes happen because of forgetting that. Wonder if your negative exponent is in the denominator. Well, it would make sense that if your negative exponent in the numerator gets switched to a positive in the denominator, the opposite would be true as well. So this rule is saying this: if you have a negative exponent and your base is in the denominator, it's going to be the same thing as moving it up to the numerator. And I know I can hear you saying, well, wait a minute, that's not even a fraction. Sure it is. Now it's a fraction. We just don't put it over 1. Okay, but it really is. It's x to the 3rd is considered the numerator of, it's certainly not in the denominator. All right, so what are the examples for this one? We did one of them. How about if we had something like 1 over x squared y to the negative 3? Now we'll note the 1 stays there, okay? Well, I'm going to do the 1. I'm going to have the 1 stay here just so that you can see what you would do if it was a different number. The x squared is what I really meant to say. The x squared is stuck in the denominator. It doesn't get to move. It stays. The y to the negative 3 has to move. If you have a negative exponent and you're in the denominator, you better move up to the numerator. And of course, we would want to write it y to the 3rd over x squared. We don't need to put that 1 there. It's kind of redundant. Wonder if you have a fraction raised to a negative exponent. Well, you really want to see it the long way? I'll do it the long way. This is what it would look like. We would say, oh, I don't want to use a, b, and negative n. What am I thinking? Let's use x and y. How about to the negative 2? So what we could do is apply our rule that says that negative 2 belongs to both the x and the y, right? And then we'd go, wait a minute. If we've got x to the negative 2, that gets flipped to the denominator, and the negative 2 becomes a positive 2. And the y to the negative 2 in the denominator gets flipped and becomes that, okay? Basically, and that is your answer. But what this rule says is you don't have to go through that much thinking. It says when you see something like xy to the negative 2, you automatically know that's the same as flipping your numerator and denominator and making your exponent positive. And then, of course, we would use our quotient power rule to come up with the same answer that we did the long way. What if we had, let's combine some rules. Let's do, what if we had x squared over y cubed to the negative 3 power? Well, the first thing we're going to do, we could do it the long way. I'm not going to stop you. We could go ahead and use power to power and all that. But I'm going to go ahead and use this new rule that they gave me, which I'm going to flip. I'm going to, oh, I'm not going to flip. Yeah, I have to flip. Sorry. I'm going to flip. It's been a long day. I'm going to flip the numerator and the denominator because that's what the rule says to do. If I flip it, then I can change this -3 to a +3. And then I can go ahead and say y to the third, power to power, it's going to be y to the 9th. X squared to the third, power to power, is going to be x to the 6th. So two different ways to get those. You can do them as you would like. One last rule to remember, anything except for 0 raised to the 0 power is equal to 1. So 5 to the 0 power equals 1. 1 to the 0 power equals 1. A million to the 0 power equals 1. If you don't believe me, try it out yourself. Except for we can't have 0 as the base. That would be undefined. All right, let's talk about some common errors first, the common mistakes over here. We talked a little bit about what a difference it makes with parentheses and one of the problems, but this is typical here. This is not the same as this. Okay. -2 to the 4th means -2 times 2 times 2 times 2. And when you put that in the calculator, we'd have what, 4, 8, 16, that would be -16. Versus -2 to the 4th means -2 times -2 times -2 times -2. That, of course, is going to be a +16. So think about that. Okay, simplifying power. Sometimes people ask me, or not people, random people on the streets. No. Students ask me, however, am I done? Am I done? How do I know I'm done? Well, when you can look at your answer and say, am I in the most simple form I can possibly get in, and say yes, then you're done. So wonder if you're working on a really hard problem and you got 4 to the -3. No, you're not done. Negative exponents are not polite. We've got to rewrite it as, even if we rewrote it as 1 over 4 to the 3rd, no. We can extend this to 1 over 64. All right, so it was fun. Lots of problems for you to practice with, but all of these rules that we just talked about briefly today need to be deeply embedded in your long-term memory, available to pull out at any time. All right, thanks for joining me, and have a great day.